Good morning. Hello, everyone. Myself, Girish Koth, and I'm going to present here the analysis and simulation of acoustics and thermal analysis of muffler. So, I will be starting with the CAD. So, here is the CAD of the muffler. So, it's simple cylindrical, and here is the inlet valve so that our gases and combustion gases will be enter from here. And this is the exhaust valve, and it is open to atmosphere. So when there is exhaust in the engine and the gases flow from the engine to manifold, it will flow through this pipe and it will and after the sound barriers and all, it will go to atmosphere from this side. So this is the isometric view of this exhaust valve, and I will be showing you the sectional view. So, okay. So in the sectional view, we can see that there are two types of nets. They are used means they are assumed that they will be providing some acoustic barrier and we will be hearing a less noise outside the atmosphere. So that's the reason we have been putting the two barriers inside, and so it will when the gases enter from the inside, so their kinetic they also contain the kinetic energy. So the kinetic energy will be damped through these barriers, and so due to this the sound will be much more reduced to the human ear and would be good to hear. So this is the CAD. So after the CAD we will move to the simulation part. So I have did the simulation in ANSYS workbench. And after I have imported here the geometry by creating the step file. And after creating step file, uh, we will move towards the meshing of the geometry. Uh, so once this meshing tab is open, so for the inside, I have given a fluid domain. So we can see that inner section is filled. So the inner section is filled with fluid domain. I have filled this inner section in the ANSYS so that there will be a particular path for the air to flow. Means we will define after in the latter post analysis when we will after the boundary condition we will show that our air is this the inner domain is our air domain and outside there is no domain. So we will get accurate results for the air, for the thermal and of course thermal analysis. So during the geometry, I have imported geometry and the material I have here I have used is a simple uh, structure steel because the most common metal and it's cheap in cost and also it's easy to manufacture of the structure steel. So structure steel has been used here. Then after the material assigned, we will go for the meshing. So the meshing I have done is simple. Firstly, I have did the auto mesh, and after the auto mesh to confirm more sizing and to increase the precision level, I have given a body sizing. The body sizing here I have given is 10 mm. I think it is appropriate because it will not give me more computational time for post processing, and also it will also give me precision level. So after carrying out few iterations, I have reached to this limit that 10 mm size is good for the meshing of the simulation. And then the method I used here is hex dominant method. The reason behind this is that as we know that hex elements have the low stiffness matrix and they have lowest value of A. So to get more precise results, I have used the hex dominant method, and we can see that there is a good amount of meshing here, and we can see the pattern is repetitive all over this. So we can see that the meshing here is good and good to go with for our further simulation, and we can move further to this. So after that, I will be closing the meshing tab. Okay, then we have to give in the setup to give the boundary conditions and the whole this simulation I have did in the fluid flow CFX tab. So actually I have solved this earlier. So it's showing like in this such way. So we can see that I have given flow analysis. Here I have assigned its inlet. Here it's outlet. And we can see the boundary conditions for inlet. Boundary details, you can see it's subsonic wave. I have given a mass flow rate, and through referring few research papers, I have found that the mass flow rate for the exhaust manifold is 0.5 kg per second. So the mass flow rate is assigned to the inlet of the exhaust manifold. Then, then again for outlet, the only boundary condition is that it's open to atmosphere. So the pressure I have assigned here is 1 bar. That is our atmospheric pressure. Then after this, uh, then I have assigned this whole remaining system as a wall. Means this whole muffler, except the inner domain, the whole CAD of the muffler is wall. Means it will and whole wall, and the condition given for this wall is no slip wall. Means there that no boundary layer will be developed throughout the wall, so that we can only analyze the flow of air inside the whole CAD. If we assign here that there is slip, so for the boundary layers may develop through inner, and we may get total different different results, and this result may interrupt if we change the material and different conditions. So that's why to keep the simulation and modeling simple, I've given here no slip wall. Then okay, then after giving the all the boundary conditions, I just exited this tab. And for solution, I have just given here starter. Then now the solution is being solved behind the screen. I just forgot to tell you one that thing that this whole simulation I have done in ANSYS Workbench Fluid Flow CFX, because the meshing is quite simple in Fluid Flow CFX as compared to meshing in ANSYS Fluent. So I have chosen to do simulation in this tab. So okay, we can see the solver exerted, but our we have reached the final synchronized point. So it means that our geometry has been our meshing has been solved, and our results are shown here. So if now we'll click on result tab. Okay, so now we will see that our results have been interpreted here. So firstly, I would like to show the streamline flow of our particles, or we can say air. So as we know that exhaust gases are not just in gases form. There are some solid particles. Also, this gas is heavy because it contains mixture of different gases like CO, NO, etc., etc. So in this through this streamline flow, we can be able to understand that how that air is moving. Air means a mixture of all gases is moving through whole throughout our muffler. So here I would like to show you the animation. So when I click for animation of streamline, and I'll do it just a little bit slowly. Okay. So here we can see that there are particles. The particles are entering from inlet wall, and we can assume that each streamline is carrying one particle. If it's mean we can assume the particle of air and all. So when the particles are here, they are coming inside in a whole group, and when they are reaching here, so some of the particles are going throughout the whole pipe, and they are going out quickly. But you can see that some particles here are creating turbulence. They are moving in circular pattern, and they are proceeding lately as compared to other molecules towards the exit of the manifold. It's because the turbulence is created. So we can through this simulation we can see that there is turbulence created, and we need to avoid this turbulence. Okay, and turbulence can be also be avoided by changing the geometry or changing the material or giving some disruptions in the CAD. So After this all is done, we can also we can also make changes in CAD, and so we can return again to this procedure and we can see and we can follow the pattern. We can see the turbulence is now created less or not. So this way we can follow an iterative way for doing the for for getting the optimum geometry for our results. Okay. Okay, now we have seen this streamline flow. Now we will be seeing the contours. So here first is a velocity contour. So as you can see that all throughout the year, I have given 3 meter per second, sorry, 4 meter per second velocity for inlet valve. So the velocity of air entering is 4 meter per second. So when it enters here, we can see there is a red region, means it indicates that velocity is higher in this region. So as soon as the a gaseous entering muffler, we can see this it's whole distributed. Means the velocity, this region we can see is blue region. Blue region will indicate that the velocity is much reduced, and the yellow region is indicates that the velocity is less than red region and it's greater than yellow region. So we can say at opening here is a yellow region, means that the velocity is reducing slowly, and we can see throughout this whole the region it's been muchly reduced up to 1 to 2 meter per second, and at exhaust again it's increased till 2.5 to 3 meter per second. So due to this whole muffler geometry, we have got helped in reducing the velocity of the air. So decreasing the velocity means we are decreasing the kinetic energy. Then the kinetic energy decreasing, so we can optimize it by decreasing more and more kinetic energy for getting better result. Also, we can get the pressure contours also. So here we can see the pressure contour is totally means opposite to velocity contour. So as we know the Bernoulli's principle that at any point the energy is constant. So where the velocity was maximum, pressure is here minimum, and where the velocity was minimum, here pressure is maximum. So throughout this geometry, we can observe the relation. So we can understand different, and we can interpret this different results through this simulation. Also, this was the thermal analysis of muffler. Now there is also second part, that is the acoustic analysis of muffler. So now it's the acoustic part. Also, acoustic analysis will show us that how are the when the gases enter in muffler, then we will be able to analyze the flow and sound parameters, and we can also analyze the transmission losses, and our main aim is to maximize the transmission losses so that less noise can be heard. So same I imported the geometry and the material. Here also I have used the same structure. Still there are no changes in material and geometry. Now here we will be giving the different boundary conditions, as our results are different, our expectations are also different. So I have also did the same meshing, hex core dominant and 10 body sizing. And after the meshing, we are going to apply total different types of boundary conditions. So I'd like to show you one thing. This is the harmonic acoustic tab in workbench. So harmonic acoustic tab will deal with the acoustic analysis of all things. So I have to do here acoustic analysis of muffler. So I have used this tab, and the other things like listening data, geometry model are same here. So now we have to give the different, for this tab different boundary conditions are available. So firstly I have given ports. So this is the inlet port, and this is the outlet port, and inside there is surface body, as we discussed previously. Then another thing, there is acoustic region. I have assigned this whole muffler as an acoustic region. So here acoustic simulations will take place and calculation will be done on this part. Then surface velocity, I have given here surface velocity of 2 into 10 raised to means 0.02 meter per second. It's the velocity of the fluid flowing through this. Then raditional boundary layers, I have given this as a means this is inlet, so I have given the raditional boundary layers. So for solution, I needed the transmission logs, absorption coefficient, and acoustic pressure. These the parameters were needed for me. So after applying this all these boundary conditions and solution parameters, I have just solved this model. And after solving this model, I have got the results. So I have got I have got the graph of the transmission loss. So we can see that the transmission loss is increasing with the frequency of the as the frequency is increasing, we can see the transmission loss is increasing. So another graph also we can get, that is the absorption coefficient. So we can see this graph shows this totally opposite of the absorption coefficient. So we can also relate that as greater the transmission loss is, there is less absorption coefficient, and we can also study at what frequency, what are the absorption coefficient we get through this graph. And the third thing is acoustic pressure. So we can see acoustic pressure is greater, means these regions of high sound, means where greater noise can be formed or created or can be heard. These are the region, and throughout the different region it's uniform. So this was the whole analysis and simulation of thermal and acoustic analysis of muffler. So so if we are designing a muffler from a scratch, we need to make a CAD, then we need to do thermal and acoustic analysis, and through results, we think that there are some there must be changes in geometry so that we can get a good results. So we need to change the again CAD and do some calculations more precisely so that we can get optimum results from this from the our muffler, and there is minimum noise and can be heard from the muffler. So through this iterative way, we can be able to optimize and design a perfect muffler for our CI and IC engines. Thank you. This was from my side.